Um, Hello, okay, let's switch to English. Salutare, bună ziua, bună seara, hello everyone. I have just started the recording, and I think like this should be the first remark or talk for today's class and for the statistical and symbolic learning. That if we ever forget to start the recording, please interrupt us and tell us, Traian, Costin, whoever is teaching, do start the recording because you forgot to start it. Okay, so I think it's important for you to have the recordings. I think we also have like the ones from last year, except for the first 4 or 5 classes, which were at the university. Okay, can you hear me well?
Yes.
Yes, we can hear you.
Okay, perfect. I've also just started sharing my screen. Probably it will take 1 or 2 seconds for you to see it. And of course, for any technical problems, let me know. Like if you cannot see my screen share, sometimes it happens. Like professors are, I want to teach, and we forget to share the screen. And it was a joke at the beginning of teaching online that a professor, it was a joke from the US university in the US, and it was like the professor had his microphone muted, his speakers were muted, and after 15 minutes of talking alone, like no slides were showing and so on, the teaching assistants tried to call him or her, and he had the phone off in order not to be disturbed during the class. And after 15 or 20 minutes, the joke is that somehow he figured it out, or she figured it out. It was a joke last year. So it seems that at least at the beginning of the semester, we're going to have the classes online. Most probably, at least for the lectures for the entire semester, we're going to see if we're going to meet for part of the labs or for the project at some point. The feedback from last year was that actually the online classes were pretty good, and I think that the attendance was larger than in previous years. And not only for the lectures, but even for the projects. And I think it was simpler for, like the feedback said, it was simpler for students to attend, to get information, feedback whenever they wanted, and they didn't have to come to the university. Okay, I hope that this year we're going to be even better in teaching online. And we're gonna see each other on Teams for the next couple of weeks for sure. Cool. So my name is Traian Rebeda, and together with my colleague Costin Chiru, we're gonna be the lecturers and the teaching assistants for this class. So if you ever want to contact us now, it's even simpler on Teams, but I like if you have important questions related to your project or maybe to some of the lectures, maybe it's simpler to write us an email. Because messages written on Teams, I think that yesterday I got about 10 messages on Teams, and I have so many chat messages. At some point, I may forget about some of them. Okay, so the lecture is going to be from 6 to 8 in the evening, and the labs or project is going to be still on Thursday from 2 to 4. And everything is going to be online, at least for now. We're going to see if we meet at the university where we'll meet. Related to the grading, we're going to have 60 points for the activities during the semester, and the majority of these will go into a project. So 40 points will be a project, which we encourage you to work in teams, in teams of maximum 4 students. Of course, you can also work alone, especially if the topic is related to your research topic. But otherwise, it would be a good idea to work in groups of 2, 3, or 4 students. Then we're going to have like 20 points for an assignment. Actually, it's going to be an assignment. It's like course and lab assignment. It depends how you want to see it. We're going to have it split in several milestones. And actually, what you're going to do here, you're going to attend a competition on Kaggle. So Kaggle is probably the most known app for the data scientists and or website for competitions for data scientists. It started more than 10 years ago. And I think we are using it for the machine learning class at the AI Master at UPB for about 6 or 7 years. So even from the beginning, and I like it a lot. So I liked it a lot from the beginning because you get engaged in a community of practice. Like over there on Kaggle, you have problems posted by companies with real-world data sets. And you have like probably right now hundreds of thousands of data scientists, some of them junior, some very senior, some of them more practical, and other ones who also publish papers and know maybe also the theory and can make innovations. And you can learn from them, like because they share their solutions. You have discussions on forums. You can ask questions. You can read the questions and the answers that are posted for the competition. So I think it's a very good way to learn practical elements of machine learning and data mining. And usually the feedback from students is that this Kaggle competition is very good. Not many students know about Kaggle before the SSL class, and most of them like Kaggle and the community and information they find over there. So like this is 60 points is very practical. We want you to understand how to use the information we teach you at the class, and not only because of course you're also going to use some elements that we're not going to discuss during the machine learning class, especially deep learning, because you know that you have neural networks in the second year. And you're going to have an entire class covering deep learning and neural networks, but you can use, of course, you can use neural networks from a practitioner's point of view. And like these are two different elements, like understanding the basic concepts from a theoretical point of view and getting a grasp into them and using them in practice. And at SSL, with this activity during the semester, you're going to have a lot of practice information and practice abilities. Okay. And of course, a reminder of 40 points. We're going to have an exam, and we're going to discuss more about the exam, and we're going to provide you some sample topics at the end of the semester. It will depend a lot on whether the exam is going to be online or is going to be in a class at the university. You need to get at least 50% from each of these two categories. Usually it's not really a problem, but there are cases when maybe like the exam might be a little bit difficult if you don't study. Cool. So related to the projects, as I've told you, you're going to work in teams of maximum 4 students. You can use any toolkits, APIs for machine learning, like any type of machine learning, deep learning or not deep learning. Actually, at least for some of the projects, we're going to like to see like baselines without using deep learning in order to have a comparison. Like even if you use deep learning in order to understand how much better, or how big is the improvement of using deep learning for your task compared to other methods. For some of them, maybe it doesn't make sense to use any other baseline. Like in computer vision right now, like for large data sets, deep learning is the way to go. Even in NLP for very large data sets, but for small data sets, sometimes deep learning is not going very well. And even today, I was talking with some people from a large Romanian company that have a data set and deep learning like BERT and transformer models have worse results than a normal classifier with features extracted using string kernels, like using character engrams, if you want, in one way or another. We're going to talk more about kernels during the class at some point. So you can use any toolkit or APIs for machine learning to solve a problem. Like here for the project is going to be a more complex problem than for the assignment from Kaggle. Most of these problems are more like research topics, like they are not practical data sets from a company. We will provide some topics which are more researchy. Like we don't have a very clear solution. You need to understand. You need to understand like which is the state of the art. To read some papers to understand which are the best solution at this moment, and then to implement your own models starting from these state of the art solutions, and maybe to improve or to combine some of them. In order to get better results or to get a better understanding of the problem, because right now there is a lot of people consider that in machine learning you need to get like from 90% to 90.1% improvement in a score. Like people are very oriented in improving the state of the art. This is how you see it. It's achieved state of the art results. But more often than not, at least in the last 1 or 2 years, people say that just pushing this state of the art percentages is not enough. You really need to understand how models are working. Or to have more efficient, like simpler models, or to understand more about the data sets, because sometimes you get a 0.1 or a 0.05 improvement, but actually that improvement is not relevant for the task at hand, is more in the noise in the data or in some specific features or biases that you have in the data. Cool. So we don't really want to see that you get like state-of-the-art results per se, but we want to see that you understand the problems that you are solving, and you are looking at some important, maybe not quantitative, but qualitative features, like understanding your results, looking at the problem from a different point of view, distinct point of view than what people have done. Of course, you need to implement several models, and we need to compare the results in order to understand why some of these models achieve better results than others. So we are not looking only to improve the state-of-the-art result, but it's important to understand like which are the results that we are getting. Okay, so we're going to post a list of suggested projects. They'll come from various fields. Like some of them will be, like machine learning. It's like theoretical machine learning, which is more complex. And then we have like practical machine learning, which is like applying machine learning in different domains, like computer vision, natural language processing, recommender systems, information retrieval, and so on. And you will have a variety of projects from these application domains. You can also propose a topic for your project, especially if it's related to your research. And I've seen in the first semester that most of you have a machine learning, an important machine learning component for your research topic. And you can also work in combination with other courses, and because Costin and I are like the teaching assistants for the NLP class as well, some of the topics that we're going to propose are going to be suitable. Like you could have only one project for both statistical learning and natural language processing in order not to have two of them. Of course, you can have two of them if you want. Like if you want to work on something related to computer vision for SSL, then you're going to have to work on a project related to text for NLP. Like if you are are there any optional students, like not from the AI master here? Okay, so I guess most of you are from the AI master, or all of you. Like this was like if you are from EC, you can work with web applications. Or if you are from the security master, you could work with something related to security. We have had students working on these topics. And even like if you are from distributed systems, last year it was a very nice project related to federated learning, which means to learn to learn from various data sets, or not having all the data set uploaded to the server where you are training, in order not to have like private information and so on a server where you train your models. It's something, it's a newer concept in ML, federated learning. And of course, if you want like data or resources, there are several repositories of where you can have data. Of course, Kaggle is also one of them. For toolkits, it's Weka in Java, but it's also scikit-learn in Python. And of course, TensorFlow and all the other ones like PyTorch for deep learning. And of course, you can use R or anything else if you want. Okay, it's related to the syllabus. The first two classes is going to be an introduction to machine learning, so today and next week. Then we're going to talk about linear models for regression. Then we're going to see the same like linear models, but for classification, and see how things change when you have several classes instead of a continuous variable. Then we're going to talk about kernel methods, and we're going to see how they can be applied together with sparse kernel machines, like we support vector machines. Then we're going to talk about Bayesian learning, and I've talked with Professor Adina Flora, and I've understood that this year at the knowledge representation and reasoning class, you have had several classes on Bayesian learning and Bayesian networks, and like we're gonna have a class expanding so Bayesian learning and then expectation maximization. We're gonna look from a different point of view to these algorithms and methods, and actually we're gonna expand a bit what we have learned at KRR. And then we're going to talk about principal component analysis, independent component analysis. And actually this year we're going to stop and we're not going to discuss hidden Markov models, because I've seen that Professor Flora already discussed hidden Markov models, and everything was clear, at least in the slides from my point of view. And then we're going to have a class on combining learning methods or on bagging and boosting methods, which are actually pretty good. At least right now in machine learning, if you don't use deep learning, you might use like XGBoost or one of these bagging and boosting models. Most of them are using decision trees, and it's a pretty good idea to talk about them as well. Okay, like of course you're gonna have the slides that we have prepared. Some of the content in these slides is taken from slides available online. like for example, this slide, it's an adaptation from Bishop's original introduction to machine learning for his book. But besides the slides, we're gonna have like we suggest you to read Christopher Bishop's pattern recognition and machine learning. Like this is one of the top books in machine learning. Like if you want to read a book in machine learning, Bishop, Murphy, or Hasty and the team are the ones which are the most important. So the most important books will be either this one or this one, and maybe the third one, Hasty, and the team from Stanford. Like the first two ones are written written for a machine learning engineer. The third one is more like for a statistician because it's called elements of statistical learning. So maybe it's gonna seem even more mathematical than Bishop or Murphy. So even Bishop and Murphy, they are very mathematical, and I know that some students say machine learning is mathematics, it's not engineering. But you really need to understand the core concepts in machine learning in order to, I don't know, like to be a machine learning engineer and not just a person who gets some code, uses a model, and I don't know, you call the API from scikit-learn without understanding what really happens over there. Cool. And of course, there are some other books. These are like Artificial Intelligence: A Modern Approach by Russell and Norvig. Like this is a very good book, but it's not core machine learning. It has some elements of machine learning. And prior to these three books on machine learning, Tom Mitchell's book from Carnegie Mellon, it was like the best book for about 15 years. But now it's a little bit old. Like the concepts from Mitchell's book are a little bit old. And there are also some practical books. Like one of them is Practical Machine Learning. This is for VECA. You can find some other books which are like practical machine learning in scikit-learn and so on in Python. Like if you want another textbook on practical stuff, there are several ones. There are similar courses at all the top universities in the world, like and like these are master classes. They are not like introduction to machine learning, the class that you would get maybe in a bachelor. And you have like the machine learning master class at Stanford. There you can look like they also have student projects in machine learning. Of course, like these are from 2018, but you can go to see the ones from last year, probably something like 2020. And you can see which are the topics which are chosen by the students from Stanford. If you like any of them and you want to work on a similar topic, this is a good inspiration. Like if you don't want to choose a topic proposed by us and you want to explore a bit, or just to explore, to see what happens somewhere else, this is a very good class. But actually, it's a huge class. Like at Stanford, I think they have more than 100 students, maybe even 200, a master class in machine learning. Then, of course, you have like machine learning at MIT, at Carnegie Mellon, and so on. Of course, all important universities who have an AI master have a machine learning class. Okay, cool. So our textbook is Christopher Bishop's PRML. This is like the abbreviation. And these are some slides which are adapted by the slides proposed by Bishop for the introduction. The other slides are also using Bishop as a textbook, and we are using the discourse prepared by Bishop, but most of the slides are original, if you want, are the way Costin and I have imagined understanding Bishop, or at least the chapters that we talk from Bishop, because we talk about like from Bishop, about 50% of the book is a part of the SSL class, not all the entire books. Okay, so we have an introduction to machine learning just to understand what's important in machine learning, to see that we have a mix of mathematics and engineering, and to understand the core concepts in machine learning. If you have undertaken a bachelor class in machine learning or maybe AI, maybe you are familiar with some of them, but we want to have these basic concepts discussed in order for everyone to be on par. Okay, what is machine learning? Probably one of the simplest tasks which we can see is like handwritten digit recognition. It's also a data set which is pretty famous, like the MNIST data set, which has handwritten digits from 0 to 9. And our objective, receiving one of these images, like an image with, I don't know, 60 by 60, let's say, pixels. We want to decide which of these 10 classes, because actually we have 10 classes, 10 digits, which of the 10 digits is part of this image. And this is a pretty basic computer vision, if you want, classification task. So actually, machine learning is used in quite a large range of domains, in pattern recognition, in NLP, in computer vision, information retrieval, data mining, and like any area of AI, and now also in other domains as well, like in security, ML, and even in systems, there are various methods using ML. Like this introduction, we also want for you to understand like the fact that we have several important approaches in machine learning. Like the first approach that was like received interest from the scientific community was the symbolic approach. Like symbolic approach was to discover rules in data, which rules could be rules written in first order logic, or they could be decision trees, they could be association rules, but in the end you had a rule which could be interpreted by a person, even by a person. So these symbolic approaches were like they had very good results at the beginning, and at least until the 70s, these symbolic approaches were the way to go. Then, actually, in the 70s, the connectionist approach, 70s and 80s, actually, the connectionist approach, which is like neural networks, was a mainstream way of doing machine learning. In the 80s, we have also the backpropagation algorithm, and actually backpropagation has risen the interest in connectionist approaches in that period, and it has made neural networks more powerful than they were at the beginning. Because otherwise, Rosenblatt proposed the perceptron, which is like the neuron from a neural network, in the 60s. But the symbolists, especially Minsky and others, they demonstrated that these methods cannot solve very simple problems like SOR and other ones. And this is why actually research in neural networks was not funded further. But in the 80s, with the discovery of backpropagation, training larger neural networks had become possible. Then in the 90s, statistical machine learning, which is what we're going to discuss in our class, was a way to go. Like with the rise of support vector machines, and not only support vector machines, but linear models for regression, for classification, and some approximation of training and online training of these algorithms, like statistical approaches were very, very good. And statistical machine learning was the only way to do machine learning research, or probably 90% of the way to do machine learning research. Until about 10 years ago, when connectionist approaches started with deep learning and deep neural networks to be the main route to work, especially on large data sets, on very large data sets. But on smaller data sets, still statistical approaches are the way to go. And even now, like there is a big debate in the ML and AI community. Like connectionist approaches are very good, but they are like a black box. Maybe you have heard at some point about explainable AI or ML. And the biggest problem with neural networks is like they are kind of a black box. We cannot really explain to a human being why a neural network took a decision or not. And there were lots of scandals. One was last year when a YouTube model for detecting hate speech stopped YouTube streaming on the most important chess channel on YouTube with a chess grandmaster who explained one of his games. Probably you can imagine what happened. Like the discourse was something, the attack on white, the attack of white on black was incredible. It was very difficult for black to regain control of the game, and so on. And for some reason, some deep learning algorithms considered it was hate speech and stopped the transmission and actually made the account unavailable for providing inappropriate content. Of course, it would be a great idea to have very good results like neural networks which are explainable and easy to understand by people, similar to statistical and symbolic approaches. And this is what's one of the main topics in ML at this moment in ML research. Okay, so this is just for you to understand that even if deep learning is a way to go right now, 10 years ago, it wasn't deep learning. It was statistical machine learning. Symbolic machine learning might also come back at some point. As connectionist models came back, maybe symbolic approaches will also come back. So it's important to understand like the core concepts, the basic concepts, the basic concepts, they are valid for all approaches, like for statistical, connectionist, symbolic, and so on. In order to be good in machine learning, you actually need to be good in algorithms and data structures. You also need to have a very good understanding of mathematics, because every ML technique is actually a mathematical model at some point. Even neural networks, neural networks are actually matrix multiplications and nonlinear functions in between. Probabilities, decision and information theory, logics, and some more, especially if you go in specific domains like ML for NLP or ML for computer vision. Again, like the key concepts, usually when we talk about machine learning, especially when we talk about supervised machine learning, we have like training set and the test set. The training set is the data on which we want to learn this mathematical model. So each ML technique is actually a mathematical model. So we want to learn this mathematical model on the training set f of x. It's a function, and then we want to make predictions on the test set. And like this is train, and this is also called the test. It's like predict or inference. So if we talk about inference, it means you make predictions. It's the same thing. Okay, if we have like a supervised machine learning, then we also have like a target vector. So for each item is a training set, we have a target. So for each x is a training set, we also have a target and associated target. And actually what we want to learn a model which is able to predict the target for new data. Yeah, this is the way we want to think about it. And actually, which are the steps? Like the first one is like pre-processing and feature extraction. Like pre-processing means to understand your data, because usually data is noisy, so maybe not all data you have in your data set is good. And feature extraction means to understand which are the important features to train your model on. Like which are, like, if you want these to be the features. Then you have the training phase, and in the training phase, you want to find, you want to train your model, and the model is like a function, y of x or f of x. And then in the test phase, you want to compare your predictions with the correct target for the data in the test set. Of course, what's important in machine learning, and we're going to see this in today's class, we want our model to be able to generalize. So we don't want to have perfect predictions on the training set. We want to have good predictions, good accuracy, if you want, on the test set. Because this, if you want, this is the training set is data the model has already seen, and these test sets are unseen, if you want, unseen or new data. So you want your model to generalize from seen data, from training, to new data, like to the test set. Okay, and now we have, again, like this is a very short introduction because we need to go to the real topics in our class. So we have various types of machine learning, and probably have to talk about them at data mining a bit. So if the training data has like an input vector and a target, like if we have this target, this is called supervised learning. If the target is discrete, or discrete means there are several values, different values or classes. So discrete or classes. Now this is what discrete means. We have classes or categories. Then it's called classification. If the target is continuous, so it's a real number between 0 and 1, maybe, or a real number between 1 and, I don't know, infinity. Then this is called regression. Yeah. So for our example, for handwritten digit recognition, this is a classification task. If we want to compute the price for a real estate, like for an apartment or for a house, this is a regression problem. Yeah, because we want to compute a price, and the price could be something starting from 0, I don't know, to millions or even more. So this is regression. Like, this is a simple explanation. Sometimes some problems which are classification are better treated as regression. Like I remember a talk from Google. I don't know if you're using Gmail and you have like, I'm not sure if this is an extension or not. Maybe you have something like a sign like this, and this is like important email. Important email. And there was a tech talk from Google research at our university a couple of years ago. And of course, it's clear that the email is either important or not important. So we have like these two categories. It's a binary classification. But actually, they obtained better results if they treated this problem like a regression. Like they opted to have a score from 0 to 1. Because like it's not very clear on email, it's either important or not important. It's more like you have a score, and it's each email is a bit important. Maybe only spam is not important, or if you get a message or from someone you don't like or you don't want to respond. But otherwise, like if you do like this and treat the problem like a regression problem, the results were better. Cool. And maybe some of you are telling right now, Brian, but this is more like the way you express, like the way you put it in two categories, like classification and regression. Okay, we understand. Like if we have categories or if we have a number, but why is it important, or why do you think that if you treat it like a regression problem, they got better results? Any ideas?
Because they got the chance to play with the threshold.
One of the things would be because they got the chance to play with a threshold, but yeah, but even like for categories, you can even for categories like most classifiers, not all of them, but many of them. In scikit-learn, for example, you have predict, which provides the most important, like the class, the most reliable class out of the two. But you also have something called predict proba, which provides a vector of probabilities. Like and you'll have like it's in class 1 with like it's important with 16%, not important with 40%, and then you can also work with this threshold. So one of the things is like you can work with this threshold and decide. But the other one is related to training. It's more related to training. I know we are at the beginning and we haven't talked about anything like how training works, but maybe some of you already know. So when you train a model, like here, when we train this model, actually what we are doing, we are optimizing. Optimizing. What are we optimizing? Do you know? We are optimizing a loss function, a mathematical function, if you want. It's called loss. And of course, you want to have like the minimum loss possible. Like you want to find a local optimum or global optimum would be great for our loss function. And the way loss functions are defined for classification and regression, this is completely different. For example, in classification, you want to have, let's say, the largest accuracy. Like you like to have the smaller number of misclassifications. In regression, actually, the loss it's an error. Like you look at the difference between the predicted score and the correct score, and this is something different. Like you can imagine, like if you make a prediction of 0.55 and the correct class is 1, the loss for regression is something like this. Usually, it's a square loss. So you get a loss even if you make a prediction, but it's not a very good prediction. In classification, if it's 0.55 and the threshold is at 0.5, then you say your classifier works very good. But actually, your classifier maybe is not working very good because it predicted very close to the margin, like to the threshold. Yeah. I hope it makes sense. So it's not only about how you define the classes, it's also about the function that you are optimizing, the loss functions that you are optimizing. Yeah. So this is an important thing. And this is more important, for example, if you have a task like sentiment analysis. Sentiment analysis in NLP usually has classes like which is the opinion expressed in this text, and the opinion is very bad, neutral, good, or very good. Like usually these are the classes. And of course you can express them like -2, -1, 0, 1, or 2. And even here, if you have a classifier, and you say like the goal label, the correct label is good, and you say it's very good, maybe it's not such a huge problem. It's either way, it's better to say that it's very good instead of saying it's very bad. But your classifier will say that if you go from good to very good, it's a misclassification. If you treat this problem like a regression, you're going to take the loss, and the loss would be something 2 - 1 power 2. And if you go over here, you have the classification in very bad, it's going to be -2 - 1 power 2. So the loss will be larger if you move from good to very bad than if you move from good to very good. So even if here we have clear classes, usually in sentiment analysis or this kind of problems where you have like classes which are next to each other, they are better to be classified in the DSM class. Then it's better to use regression and not classification. But again, it takes lots of experiments in order to decide which is a way to go. Cool. So this is supervised. two main types of supervision: classification and regression. A kind of clear definition, discrete versus continuous, but in real world, I just wanted to show you that this definition, like, is not always the way to go. If your training data only has like input vector and you don't have any targets, like you don't have any labels, then this is called unsupervised learning. And actually, unsupervised learning is great, and it's maybe the way to go, because like people and animals are able to learn without supervision. Like you don't have an animal and the animal learns that I don't know, you have food, and you see, like, you know, right now a deep learning model or a model needs to see lots of images of cats and dogs, like, I don't know, tens of thousands of cats and dogs in order to understand what a cat and a dog is. A human person usually sees one cat and one dog. Like, you don't need to have so many labels on data. So it's good to have lots of data, and this is called unsupervised learning. And you can use clustering in order to determine similar examples. You can use density estimation, like to see the distribution of the data. You can use have visualization algorithms like PCA or TSNE, in order to see how the data looks like in 2 or 3 dimensions that a human can understand. And at least in the last couple of years, deep learning has worked great on supervised learning, and not only deep learning, statistical learning as well. But in the last 2 or 3 years, we are looking at methods for unsupervised learning, but also for something called semi-supervised. Semi-supervised says, okay, I have a smaller data set which is supervised, which has labels, and a larger one with similar examples, but where I don't have any labels. And maybe we can find an algorithm which is able to automatically infer or label, infer the labels, yeah, or compute the targets. Of course, this algorithm makes some errors, like it's not perfect. Cool. And now, like, and like we need to stop a bit. Like these are the core, because otherwise, I'm gonna also tell you that in the last 2 years, also something called self-supervision. Self-supervision is very important. Self-supervision says maybe we can imagine a task even if we don't have a clear target. We can imagine artificial tasks. For example, in NLP, the transformer models use something called masked language modeling. Like, I'm giving you a phrase with many words, 500 words, and I'm taking out some of them. Like here, I'm taking out a word, and I want to predict which is a word that I'm thinking I have taken out by looking at the words in the context. Like, I have all the other ones, and I would like to the model to be able to predict which is a word I have taken out of the context. Yeah, and this is called masked language modeling. And there are similar models in the last year or so for vision as well. Cool, but now let's get simpler. Like I have tried to teach you, to expose to you to the most important concepts, and not only the ones which are like mainstream for several years, like classification and clustering, but also to the ones which are pretty new, like in the last couple of years we have advances in research, because I think it's important at least for you to know about them. And if you are interested, or if you think some of this research would apply for your research project, you can go and read more about it. But now let's get back to simpler and more basic ML stuff. For example, if we have the input data and the targets, and like here we have images and labels as targets. If we have this association, this is a classification task, and here we have like animals from each image. Otherwise, if we are if we are provided only with the images, we can cluster these images, and we'll get something like this. Like, clustering is not perfect, Yeah, for example, here we have cats and dogs. Also here we have cats and dogs, but here are like black cats and black dogs, and here are like brown cats and brown dogs. And here we have a cat which is mixed. It's white and brown. But in some of these clusters, you only have bears, and then it's pretty good. And the last thing, like, and this is like taking on a slide on its own, just to understand that it's also very important. And actually, this is a way animals and humans learn. It's called reinforcement learning. Actually, reinforcement learning, we don't have a data set with items and so on. We have a complex environments that we need to explore. And we need to take actions. For example, should I learn machine learning or should I not learn machine learning? Should I enroll in an AI master to learn machine learning, or should I learn machine learning on Kaggle and online? And lots of other actions, yeah. So we have a complex environment and actions, and like we have an agent which needs to undertake a list of actions, and at each moment you take an action, and you get some rewards or punishments from the environment. So we don't have any training examples, but we get this feedback from the environment. So we have an agent, if you want. The agent has some actions on the environment, and the environment from time to time, not always, responds with rewards. And rewards are either positive or negative, and they could be punishments if you want. And we need to understand how to explore this environment in order to get the highest reward possible in our life, if you want, or in the life of our algorithm, our ML algorithm. Cool. And here it's, of course, an important trade-off between exploration and exploitation. Like in order to get rewards, you need to explore. But if you explore too much and you just go randomly in all the directions, you won't be able to find the best rewards. So this is like called exploitation. So you need to explore, but at some point you also need to take the rewards that you have seen and to understand the basic situations, the situations that provide you good rewards. Cool. So this is about reinforcement learning, and reinforcement learning is actually the way to do complex machine learning in real world environments, like not on synthetic, on data sets, or on very simple tasks like maybe artificial or tasks taken out in the environment. Because even these images with animals, they are from our real world, yeah. Like when we see a dog with a ball, we get a larger context. A model, a supervised machine learning model, maybe is not able to get this context because the model never interacted with this environment. The model won't know that this is a ball. The model will know that there are some yellow pixels in the image, and it doesn't understand that the dog plays with a ball and so on. Like if you want to have complex understanding of environment, you need to use probably reinforcement learning. And now we get back to our slides. So this was like the introduction to the key concepts in machine learning in general. I hope that everyone has found something new. For those of you that already knew some of this stuff, maybe it was a good refreshment, let's say. And now let's go into our class. And now we talk about polynomial curve fitting. This is a regression problem, and actually we want to understand again the core concepts in machine learning. So what happens here is that we take the sinusoidal function. So the green function is called the real function or the objective function. So this would be the function we would like to compute. The model we would like our model to learn. But what happens? We have 10 data points here, the blue circles. And these blue circles, they are sampled from the sinusoidal function. But as you see, some of them are on the sinusoidal function, like this one and this one, they are on the sinusoidal function. But other ones, like this one, they are very far away. Why? What happens? Why do we have, like, this is a data set that we would like to use. And we say it's a data set sampled from a sinusoidal function. Why do we have these differences?
Because of noise?
Yes, exactly, because of noise. So actually, this is the first lesson. The real world data is noisy. Even if it's from sensors, if it's from labels put by humans, we always have noise. It's almost impossible not to have noise in big data sets. And this is why, like, this is a synthetic data set, but Bishop wanted to make it very similar to real world data sets. Yeah, because otherwise we could have sampled from the sinusoidal function per se. So we sample from the sinusoidal function and we add a Gaussian noise. Yeah, Gaussian noise, like plus minus a variance. Yeah, and this variance is not very big. Yeah, like, it's kind of small. Yeah, it's smaller than 1. I don't know, it's 0.2 or so. The larger the noise, of course, the more scattered the points would be from the objective function, from the green function. Okay, so this is a mock-up, but very similar to real-world data. We have 10 data points from a sinusoidal function, which are affected by noise, and this is what really happens in all data sets. You cannot assume your data sets don't have noise. Only if they are very, very small and they are annotated by several experts, and you have something called the inter-rater agreement of 100%, which happens very infrequently. And now we say we want to compute our model, and our model is like the function y of x and w. Now here we're going to have the following convention for notations. If you have something in italic, italic means that we have a scalar. If we have a value lower cap but in bold, this means that we have a vector. If we have an upper cap in bold, this is a matrix. Yeah. So A would be a matrix. If you ever have questions, you can ask me or Costin. Cool. So here we want to make we want to learn this function, and we say this function is going to be like a sum of polynomial functions. We're going to talk more about this 2 weeks from now, because like this is regression. This is a linear model for regression, but we only talk the basic stuff. Actually here we're going to have several polynomials, like the first one is x power 0, the second one is x power 1, and so on up to x power m. Therefore we're going to have m plus 1 polynomial functions in our model, and each function is multiplied with a weight. So w is a vector of weights. They are called the weights of the model. And we'd like to optimize, we'd like to learn these weights in order to have the best function, the best polynomial curve fitting. So it's called polynomial regression because we have polynomial functions, x power 0 up to x power m. Of course, we can write it, we can write this like even simpler. It's a sum from which j goes from 0 to m, from wj x power j. And we're going to see that we can even write in a simpler notation using algebraic notation, so multiplication of arrays. But right now it's simple enough to do it like this. Cool. So we have the weights, and the weights are in front of the polynomial functions. And we have actually we have a combination of these polynomial functions in order to approximate our data set, our training data set. And now we say the following thing. We have this training data set, and actually what we want to, so it's an optimization problem. I've told you, we want to minimize a loss or an error or loss function. So each machine learning method actually needs to optimize an error or a loss function. In our case, if it's an error or loss function, you need to minimize the error or the loss. No? And this is like the error in the model. So the error in the model, the weights are the parameters of the model. And the E is from error. The error of the model or of the weights, if you want, we can define it like this, and this is called squared loss. Squared loss or squared error. The error is always the difference between the correct target. So for each point n, so n is a point in our training set out of the 10 points, the error is always the difference between the correct target and the predictions that we have made. So y of xn and w is the predictions that we have made, and this value in absolute value, of course, in modulo, is the error. So this is the error, and here we have a squared error because we have the error power 2. And usually, like we don't need to use squared error. We can use normal error, but usually in practice we are using squared error. We're going to see why we are using squared error, because when we optimize a specific function, like when we use maximum likelihood, we'll get to the squared error out of the process of minimization. So what we want to compute the minimum errors that we can have. So we want to minimize this function. And we want to compute the best weights. The best weights are W star, such that the error for W star is the minimum out of the error for all the weights that we can compute. Cool. And this is called like sum of squares error function. So we squared error, and we have a sum over all the points that we know. The points in the training set, and this is why it's called sum of squares error function. And now the question would be, which is the best models that we can compute? The models that we can compute, now it's a red function, a red curve. And now if we say we only allow 1 degree of freedom, so m equal to 0, only 1 degree of freedom, what we will get? So like this is a function. It's a function which is parallel with the axis OX. But it's not equal to 0. Why?
Because it is equal to W0.
Yeah, it's equal to W0, but W0 is learned from the data, if you want. Yeah. Actually,
because the noise in the data kind of moves this line up.
Yeah. So the noise in the data is a little bit biased. So the noise is sampled from a Gaussian. Like if we would have an infinite number of points, or a very large number of points. So if the n is the number of points. So n is number of points. This number, yeah, n is the number of points or points in the training, or number of samples in the training data. If n goes to infinity, this curve would be like this, would be equal to 0. Because the noise is Gaussian, and if you have an infinite number of points, you're going to see that it goes to 0. But because n is 10 here, we have a bias, and the bias says here the noise was a little bit shifted up. We had a little bit positive noise. Yeah, this is what we are saying. So if we take the average, what happens if we take the average of all these points? This average would be equal to this bias. Yeah. So the average of all these points is positive. And now we say 2 degrees of freedom. So m equal to 1. It means 2 degrees of freedom because we have x power 0 and x power 1. So it's still a line, but now we add an extra degree of freedom, the angle. Yeah, and this is like the best fit that we can get. Now 4 degrees of freedom, like 4 polynomials, and it kind of looks like a sinusoidal. It's pretty good, yeah. And now we have 9 degrees 10 degrees of freedom. The largest polynomial is a 9-degree polynomial. What happens over here? Why does this happen? Is this good machine learning? Is this good? Is it a good generalization?
It overfits.
Yeah, so this is called overfitting. Yeah, this is, if you want, in numerical methods. How do you call this? A function that goes perfectly through all the points. Numerical methods, anyone? I think that you have studied these numerical methods. I'm pretty sure. It's called interpolation, no? Or spline, if you want. So this is interpolation or spline. The error in the training set is 0, but actually for new points, like if you take, if you want to make a prediction over here, the error would be huge. Like you would have a very big error, very far away from the sinusoidal function. So here you don't have no good, generalization is no good. Generalization, not good. So this is not a good idea for machine learning. Yeah. So, and this is called exactly overfitting. So overfitting, like if we have a training data set and we also have a test data set, another data set, we don't know. We haven't. We don't have the points here. We don't care which are the points, but they are from the same interval, from 0 to 1 or for x. And now here, what happens? This is the number of functions, the number of parameters of the model. Yeah, the number of polynomial functions. And you see, as we increase the complex, this is like the complexity of the model increases. As we increase the complexity of the model, the training error always decreases. Yeah, the error decreases until it reaches 0. But when we look on the test error, we see that it decreases, and at some point, somewhere over here, it starts to increase, and here it goes up a lot. Yeah. And here is something called root mean square error. So the mean square error is the one that you, the sum of squares errors is the one that you knew. Mean square error, it's a mean, so it's divided by n, it's divided by the number of data points. And root mean square, you also add a square root. So root mean squared error, we have it depicted over here. And this is one of the standard errors in machine learning. You're going to see it a lot, even on Kaggle. Cool. So this is overfitting. So when we get to this situation, this is called overfitting. But even here, it starts to overfit. Yeah. So overfitting doesn't mean you need to have such a huge difference. Yeah. From here on, we start to see overfitting. And if we look at the polynomial coefficients, actually, this is what happens. So for m equal to 0, the coefficients are small. M equal to 1, again, kind of small. M equal to 3, okay. And then if we go to m equal to 9, these coefficients explode both to the negative and to the positive. Like they become very, very large in order to interpolate through all the points, like to memorize, if you want, all the points in the training set without being able to generalize. Yeah. So a solution to overfitting, so there will be several solutions we're going to see throughout the class. But in this introductory class, the first one would be maybe to have more samples in the training set. So if the number of samples in the training set is at least 1 order of magnitude, so it's 10 times larger than the number, the complexity of the model, the number of degrees of freedom of the model, then we won't have overfitting. Yeah. So this would be one way of removing overfitting. The other one is to use regularization. So each model has a way of adding regularization. Even deep learning has a way by adding dropout, for example. So let's see what these two methods mean. Like the first one, increase the size of the training set. So even if we have 10 degrees of freedom, if we have 15 points, it kind of looks okay-ish. Yeah. If we have 100 points, as I've told you, 1 order of magnitude difference between them, so 100 versus 10, it looks almost perfect. Yeah, the red function, the ones that we compute, y is almost perfect to the green target function. Okay, but it's not simple to get data. Like sometimes data is, we have 10 points, and this is also data we have. It's difficult to make to get more labeled data sets. Yeah, yeah, the next way to do it is to add regularization. So instead of having only the sum of squares error, we have seen that the problem was that we had those very large coefficients, and the way to do it is to use a regularized error, which is sum of squares, and we're going to see that this is called error in the data. This is the actual error in the training data, and we add a regularization. This is norm 2 pow2, if you want. So it's the norm 2 out of the weights, and this is actually the error in the model. So we don't allow the weights to have a big norm. If you don't remember, the norm is defined by so if W here is body, so it's a vector. Is defined like this. So norm 2 is defined by W1 pow2 plus W2 pow2 plus so on and so forth, Wm pow2. And of course, for us, it started from 0, so it would be W0, W1 up to Wm. Yes, so actually the weight is square root out of sum of Wi with I starting from 0 to m. I don't know, it's a dimension of our array. But actually regularization doesn't always use this norm 2. So this is called the Euclidean norm. Euclidean norm. You can use some other norm as well. So actually you could use any norm here. You could use norm K. Yeah, like if you want Manhattan norm when K is equal to 1, I think, yeah, K equal to do Euclidean norm, or even K equal to 3 or more. Or you can use a combination. We're going to see that some models use a combination of regularization. And actually, in this situation, when we add the regularization, we are adding a regularization coefficient. So lambda is called a regularization coefficient. Like we need a way to tell which is the error which is more important. So this is a loss function we need to minimize. Do we want to add a larger importance to the error in the data or to the error in the model? Like, do we want to penalize the model more or do we want to penalize the data more? But now we have another problem. So we're going to say, but Ryan, now we have added another parameter. Like if until now the parameters of the model was only the weights, an array. Now we have added another parameter, which is lambda, and this is called, is not really a parameter of the model. So this is a parameter of the model. Parameter of the model. How do you call lambda? Do you know? It's actually called a hyperparameter. So it's not a parameter in the model because the model only has a weight. So we need to find a linear combination of polynomial functions, and the weights provides this linear combination. Lambda is a hyperparameter, so it's not in the model, but is in the way we express our loss. So different models will have different hyperparameters. And now, but it's actually like a parameter, so we need to find the optimal value, so the best value. And now we're going to say, okay, Trent, but how do we do it? And usually for hyperparameters, the way to do it is to use something called grid search. Or you need to use some search methods. Or you can also use other optimization techniques. And grid search actually says we're going to take several values. Like we're going to take some smaller values and some higher values for lambda. Yeah. And we say that logarithm of lambda is -18. So actually, lambda, is it a large number or a small number? If logarithm of lambda is -18, which is a value of lambda? Or actually, what we want to say is like it's a small number. No, it's less than 1. So actually, here lambda is less than 1. because otherwise logarithm of lambda would have been a positive number. Cool. So lambda here is small. This is a way of picking lambda. And here lambda is pretty high. Yeah. Here lambda is, what value do we have from lambda? It's equal to 1 now because logarithm of lambda is equal to 0. So what do we have here? How do you call this? Because we have seen overfitting. This is called
underfitting.
Yeah, this is like on the other extreme. This is called underfitting. Yeah, as we have overfitting, we also have underfitting, and you have also seen it here. So this is overfitting in the model, and this is actually up to here. This is underfitting. So when the model has a large error on the training and on the test data set as well. So you can decrease the error both on train and on test. So this is underfitting. And here in this slide is an example of how you can get to underfitting if you put too much weight on the error in the model. So here actually you're going to put so much importance on the error in the model that you won't be able to learn anything, because actually what you will learn to minimize, you learn to minimize the norm. So if you minimize this norm, all the parameters will go kind of to 0. This would be the way you should think about it. Yeah. And actually, this is what happens. Like if you look at the logarithm of lambda and the root mean square error, again in this part is clear underfitting. Sorry, in this part, what do we have? In this part.
On the left, we have overfitting.
Yeah, so lambda is very small. If lambda is very small, we have overfitting. Yeah, because you can imagine, like if lambda is very small, if lambda, for example, if lambda is equal to 0, you don't have regularization. So here, when lambda is equal to 0, no regularization means overfitting. You have seen. So lambda equal to 0, so you are missing regularization, or very small, you have overfitting. And here when lambda is it goes up, is very high, you have underfitting. So from here on, you're going to have underfitting. Cool. And now we need to find the optimal value for lambda as well, like for hyperparameter. How you do it? Grid search says we should pick several values. Like we should pick several values and train several models. Maybe you need to have a validation set and maybe use cross validation. This is something you're going to discuss next week, what cross validation means. Cool. And again, looking at polynomial coefficients, like here lambda is 0 now because logarithm is minus infinity. So again, it's overfitting. Here it's underfitting, and here is somewhere in between where we have pretty good values. Yeah. Even if the model has 10 degrees of freedom and you only have 10 points, we have a pretty good a pretty good fit. Cool. So this was like the first part of introduction to machine learning, like the core concepts in machine learning. From now on, we are able to talk in the words, if you want, of machine learning. But we still need to learn a little bit of probability theory. One way of looking at statistics, especially in statistical machine learning, is to understand probabilities. Yeah, one way of thinking about models is to think about random variables and the distributions of probabilities. And now we have like two random variables here. So the first random variable would be the box. So one random variable would be the box equal to red, let's say. We pick one of the two boxes, so random variables. So the first one would be box equal to red or box equal to blue. So this is a box random variable. And the other one would be the fruit random variable. And we have two types of fruits. Let's say the orange ones are oranges and the green ones are apples, if you agree. So these are the fruits. So we have two random variables. Why do we say we have two random variables? Like, we want to talk about the core concepts in probability theory. So when we have at least two, we can talk about joint probability. So joint probability is a probability of x being to xi. So the first random variable here would be like the box being blue and the fruit being an orange. And here what we say, we need to count. Like, if the box is blue and fruit is orange, box is blue and fruit is orange, which is a probability, is a joint probability. So we say we need to count. It's how many items we have. We have one item divided by the total number of choices. And the total number of choices here are 1, 2, 3, 4. And here we also have 8. So divide by 12. So the probability, the joint probability of box being blue and the fruit being orange is 1/12. Of course, we can build all the other 3 ones, and if we sum up all these 4 probabilities, we're going to get to a correct probability distribution. We're going to get to 1. What kind of probabilities are these? Like, what kind of random variables are these ones? These are discrete random variables, because we can also have like continuous random variables. Yeah. So if you want, like, these are classes. We have 2 types of fruits. We have 2 types of boxes. Yeah, we have like a discrete or categories, but we could also have like continuous random variables. So in this case, where we have counts, we have discrete random variables, and then we can have like the marginal probabilities. So if we have a joint probability, marginal probability means the probability of only one of the random variables, like probability of the box being blue, let's say. And we also have like conditional probability, which is a probability of picking an orange from the blue box, given that the box we pick from is a blue box. Yeah. And there are 2 important rules in probability theory. The first one is the summation rule, the sum rule, which says that if we have the joint probability, in order to compute the marginal probability, we have to, this is called marginalize out the other random variable. So if we have the joint probability, what we need to do, we need to marginalize out the other random variables. If we have several of them, we need to marginalize out all of them. What does it mean to marginalize out? It means to take the joint probability for all the cases. So if we have L, in our case, L categories, we need to take all the L categories for the second random variable. Cool. And then we also have the product rule. The product rule says that if we want to compute the joint probability, we can express the joint probability as being P of y given x multiplied with P of x. And of course, we can also write it the other way around, P of x given y multiplied with P of y. Yeah. So the sum rule and the product rule, we can write them even more simpler like this. So sum rule says if we want to compute the marginal probability of x from the joint, we need to sum out over all the possible picks that we can take for the second random variable for y. And the product rule says that the joint probability is the conditional multiplied with the marginal. Cool. And the last thing we want to talk about is the fact that we will use Bayes theorem a lot. So Bayes theorem says that if we have a prior, this is called the prior random, the prior for the random variable y. So y is a random variable. We have a prior probability distribution. And for example, we have the probability of raining. Sorry, the probability of the grass being wet. And now we find out something new. So we find out about a new event, a new random variable. So y would be grass is wet. Or maybe let's go for another example. Y would be the fact that it's raining outside. And if you are in Bucharest, the probability of raining in one day, let's say, which is the probability of raining today, the probability of raining today would be the number of rainy days on average over I don't know, over 100 years. Probably it would be, I don't know, 1 in 5 days, 1 in 10 days, somewhere, 1 in 5 days, let's say, I guess. So this is if you don't know anything else. If you look outside and you see that it's very cloudy, or if you hear a thunder, so X, it's another random variable that provides you extra information about Y. So the two of them should be interrelated. If they are not interrelated, nothing changes. But if they are interrelated, the posterior, this is called posterior probability for Y. The posterior will change. So which is the probability of raining given that we hear thunder outside? And Bayes said it's a probability, this is called like the likelihood, this is called likelihood. It's likelihood, the probability of hearing a thunder given that it rains, like how much interconnection do we have between the two random variables the other way around, multiplied with the probability of raining, because if it rains very infrequent, like if it never rains, you can hear thunders, but it will never rain. Yeah, maybe you hear a thunder from somewhere far away. Yeah, divided by the probability of hearing thunders, because it's important how often you hear thunders. If you want, like here, P of X, you can also look at it as a normalization parameter. Yeah, because it's a sum over all the values for Y, like raining and not raining, out of this term. So actually what Bayes theorem says, if we want to compute, if we find some new information, like if we have a new random variable X, and we want to compute the posterior probability, the posterior it's actually not equal, but it depends on the likelihood multiplied with the prior for that random variable. And now we get back to our example, and we'd like to compute some probabilities. For example, given that we know the marginal probability from picking from a box, like in 40% of the times we pick from the red box, of course, is a reminder, box equal to blue, it's 0.6. We want to compute which is the probability of selecting an apple or an orange, knowing that you pick from the red or the blue box. Which is the probability of fruit being an orange, given that the box is blue, let's say. Then which is the probability the fruit is an apple, given that the box is blue. Which is the probability the fruit is an orange, given that the box is red. Which is the probability of fruit is the selected fruit is an apple, given that the box is blue. So we'd like to compute these 4 conditional probabilities. In this situation, can you tell me like which are? Let's see how we can do it. We can visualize this. So which is a probability the fruit is an orange given that the box is blue? It's 1/4, no? We have 4 fruits in the blue box. Which is the probability of a fruit being an apple given that the box is blue? It's 3/4. Therefore, if we sum the 2 up, we have this should be a correct probability distribution, and it is. So the sum it's up to 1. Which is the probability that the fruit is an orange, given that we pick from the red box? It's 6/8. So it's again 3 divided by 4. Which is the probability of picking an apple from the blue box? It's 2/8. It's 1/4. Cool. So this was the first part. now we have the second part. The second part was, which is the probability that we select an orange, which is a probability that the fruit is an orange. Any ideas?
We marginalize the box.
Yes, so in order to compute the marginal probability, we need to marginalize out the box. So the box has two values, blue and red, out of the joint. So the joint would be the probability that the fruit is an orange and the box is blue. And now we apply, so actually here we apply the sum rule, and now we apply the product rule. The joint probability, it's actually a sum sorry, this is a box. So actually here we can write that it's the probability that the fruit is an orange and the box is blue, plus the probability that the fruit is an orange and the box is red. And now we apply the product rule. So the product rule can tell us how we compute this joint probability. So actually here we have, it's a probability of fruit is an orange given that the box is blue, multiplied with the probability that the box is blue, no? Plus the probability that the fruit is an orange given that the box is red, multiplied with the probability that the box is red. Okay, and now I think we know all the values of the probability that the fruit is an orange given that the box is blue is 1/4. The probability that the box is blue is 6/10. Plus the probability that the fruit is an orange given that the box is red is 3/4. Multiplied with the probability that the box is red is 4/10. So here we get, so it's 3/20 plus 3/10. So it's actually 9/20. It's a little bit less than half. So the probability of selecting an orange is a little bit less than half. Also, we have more oranges, than apples. So we have 7 oranges and only 5 apples. But because we have a higher probability of picking the blue box, the probability of picking, the marginal probability of picking an apple is higher in this situation. Cool. And now the last question was, knowing that we have selecting an orange, so we know that we have selected an orange, which is a probability it came out from the blue or the red. So this is what we need. We need to compute the posterior probability. Yeah. So we know the prior. So the prior, the probability that the box is blue, we know that it's 60%. But we want to compute the posterior. So we have found something new. We know that we have selected an orange, and we would like to compute which is the probability, the posterior probability. And now we need to apply Bayes' rule. So Bayes' rule is actually the probability, the likelihood, the fruit is an orange given the box is blue, multiplied with the probability that the box is blue, divided what we have just computed. The marginal of the fruit being an orange. Actually, we get the fruit is an orange given that the box is blue. The fruit is an orange given that the box is blue. It's 3/4. The probability of the box being blue is 60%, and the probability the reverse probability for the fruit being an orange is 20 divided by 9. So actually here we get 2. Something is not really good. Fruit is an orange, box blue. Sorry, fruit an orange box blue is 1/4. Fruit an orange box blue is 1/4. It's not 3/4. Because we would have gotten a probability of 1, and it wouldn't have made sense. So 1/4 instead of 3/4. So let's write it again. So 1/4 multiplied with 6/10 multiplied with 20/9. So this one goes up with this one. Cool. So it's 3/9. So it's 1/3. So it's 30% that it came from the blue box, the orange. And of course, we can also compute which is the probability that it came from the red box. You can compute it, but because it should be a correct distribution of probability, it should be 1 minus 1/3, and it's 2/3, and you can compute it at home if you want. Okay, so if we know that we picked an orange, with 66% we have taken it from the red box, and of course the red box has more oranges, and with 33% it came out from the blue box. Cool. So this was just a simple exercise of using probabilities. And now to finalize, like we still need to talk about 2 or 3 elements related to probabilities. The next one is like probability density. The density of a probability, like the probability of X being part of an interval, is the integral out of. So this is a probability distribution. It's continuous, and this is called like the cumulative probability distribution. The cumulative probability distribution, when you go from -infinity to +infinity, should be equal to 1. Yeah. So if you want, is the integral from -infinity up to z out of p of x. So it's the area that we have until a point p of x, until over here. And if we go from -infinity to +infinity, the cumulative probability distribution should be equal to 1. So this is for continuous random variable. So here p of x is a continuous random variable. In this case, we have this upper p of x, which is a cumulative probability distribution. And we also want to discuss a little bit about expectations of functions. So here is the expectation of a function f under a specific probability distribution. Yeah. And actually, when we talk about the expectation of a function, it's the sum of the value of the function in point x multiplied with the probability that we have for z point x. And this is like for discrete random variables or discrete probabilities. If we have a continuous probability function, then it, of course the sum transforms into an integral. We can also have it like a conditional f conditioned on y, where y is another random variable. And this is expectation over x, because now we have 2 random variables, x and y, or two distributions of probability, if you want, and we want to know that it's conditioned by y and the expectation is over x. One simple way about thinking of expectations is to have like this is called the approximate expectation for the discrete random variables. It's actually the average out of f of x of n. So if we have n points, you see it's the average because we divide by n. And actually, this is the expectation of the function. It's called approximate because it's the expectation of the function under what distribution of probability? what is
uniform distribution?
Uniform distribution, yeah. So under uniform distribution or a perfectly random if you're on distribution, we would get this approximate expectation. Because if it's a uniform, if this distribution it's uniform, each point has the same probability of appearance, yeah, and this is why and which is a probability. If we have n points, it's 1 over n, no? So the uniform distribution, if we have n points, if each of these n points has 1 over n probability, and this is why we say this is an approximate expectation. An approximate expectation is the expectation under the uniform distribution. Okay, so first we have expectation, and then we talk about variances. Actually, the variance of a function is the expectation between the square value between f of x and the expected value of f of x. And you can write this, it's the expected value out of f power 2 minus the expected value out of f everything power 2. And why does this happen? Like if we expand over here, so if we expand this power 2, we get that it's the expected value, and actually this expected value is under x. Yeah, it's taking into account x out of f power 2 of x minus 2 times f of x multiplied with the expected value out of f. I'm going to write it like this because it's simpler. I'm missing out the x plus expected value of f power 2. And actually, what's important to notice, this expected value, it's actually it doesn't depend on x anymore because it's already the expected value. So it takes out x. If you want, it's a number. It doesn't. If it has any other dependencies on, I don't know, y, z, and so on, for sure it doesn't depend on x. So expected value of x of f it doesn't depend on x. Therefore, if it doesn't depend on x, here in this term, the only one that depends on x is f of x. So actually here, what we say, it's expected value out of f power 2 of x minus 2 times expected value of f. Yeah, because we apply multiplied expected value of f, which doesn't depend on x, therefore it doesn't change, plus, sorry, move a bit, plus expected value out of something that doesn't depend on x is like a constant. It's just expected value power 2 out of f power 2. So actually what happens, this term will go away with these two, with the 2 in front that we get over here. So it's actually expected value out of f power 2 minus expected value of f power 2. Yeah, expected value of f power 2. Okay, in a similar way, if we have 2 random variables, x and y, the covariance says how much they vary together, like the expectation of x multiplied with I minus the expectation of x and the expectation of y. Like if the 2 distributions, they vary the same, like they increase or they decrease the same, then we're going to have as bulk covariance. If they are very different, we'll have a large covariance. So if covariance of x and y is 0, x and y are uncorrelated. Therefore, if x and y are independent, then the covariance is 0. Yeah. And now the most important distribution of probabilities that we're going to talk about, Gaussian distribution. Probably, I'm sure that all of you know. So it has a peak. It's called a mode. It has only one mode. The mode is on the mean. So mu is a mean. Sigma power 2 is called the variance. or the squared standard deviation. So sigma is called standard deviation. Mu is a mean, and actually it's a distribution from the exponential family. Was very important. So the mode is on the mean between the mean minus sigma and plus the mean plus sigma. We have about 70% of the cumulative probability distribution. And actually, the standard deviation, like if the standard deviation is small, what happens if we have a small standard deviation? So if the standard deviation is small, the Gaussian distribution will be very sharp. If the standard deviation, so this is if standard deviation goes to 0, it's very sharp. If the standard deviation is high, it's gonna be the other way around. Okay. The Gaussian distribution is always it has a positive value. The expectation, so the expectation of a distribution is under function identity. So it's under the identity function. So the expectation value of the Gaussian, it's actually the mean. So if you want the expected value is if we describe with only one point, the point would be the mean. And the variance is actually the expected value out of x power 2, identity power 2. It's actually, so the variance is expected value out of x power 2 minus e of x, expected value of x power 2. So it's actually the standard deviation power 2. So the variance, when we talk about the variance, it's actually the standard deviation power 2. And these are the two parameters. So if you see, the Gaussian distribution has two parameters, the mean and the variance, or the expected value and the variance. We're going to stop here. We're going to continue next week. So Gaussian distribution, this is only a one-dimensional Gaussian distribution. So the only dimension is x, but we could have a multi-dimensional Gaussian distribution. It's called multivariate Gaussian distribution. So here x, it's an array. It's a vector. If it's a vector, then mu is also going to be a vector because we need a mean value for both dimensions or for all dimensions. And the standard deviation or the variance shifts into, this is called the covariance matrix. Covariance matrix. The formula is pretty much the same, as you can see. Here we have these a number of dimensions. This is probably the most important change. Otherwise, here it's you see it's always x minus mu power 2, and here it's x minus mu power 2, but we have the reverse of the covariance matrix. And actually, if you want to imagine, if you haven't imagined a multivariate Gaussian, this is a two-dimensional Gaussian distribution. This is a mean. So the mean here, it's an array. It's mu1, mu2. If you want one value for each axis. And this is like plus minus 1 standard deviation on the two axes of the Gaussian. So the Gaussian distribution has two axes. Not always the axes of the Gaussian distribution are the same as the axes of our system. Like the variance can be shifted. Yeah. And actually, the covariance matrix tells us which are the variances and how we have this shift by taking into account the system of coordinates that we are part of. And it's the same. Like here, it's plus minus 1 standard deviation, plus minus 2 standard deviation. This is what we mean when we have this two-dimensional representation. Cool. So this was the first machine learning class as an AI master. We're going to continue next week with the introduction. If you have any questions, I'm here. Otherwise, I'm wishing you a pleasant evening. See you next week. And next week, we're also going to have the projects, a meeting about the projects from 2 to 4 for NLP and for SSL.
I have a question.
Sure.
I was was wondering if for the project hours the attendance is mandatory, and if not, can the project hours be moved to a different hour?
The presence is mandatory only when you have to present your project. Like you're going to have about 4 milestones, and you need to be there to present your milestone. And of course, if you want to attend to see what your colleagues have done, like this would be nice if you want to learn some new stuff. But otherwise, you only need to present your work. Yep.
Okay.
Actually, otherwise, for me and for Kos, it's pretty difficult to move later during the evening. Both of us have a small child, so if you hear some wabbling or crying, I'm sorry, but I'm teaching from home, and in the evening it's a little bit difficult for us to go over 8 or even close to 8.
Okay, I understand. Thank you.
Okay, thank you. But anyway, if for some reason you cannot attend in 1 week from 2 to 4, you can write us an email, and we can meet in another day, maybe around 6 or 7. But at least last year, the students didn't have many problems attending the milestones, especially as the last milestone usually is during the lectures. Like in the last week of the semester, Professor Troushan also offers us a class, and we have like 4 hours of projects starting from 4 going to 8 in order to look on the final versions of your projects. Any other questions? I guess not. Then I'm wishing you good evening. See you next week.
Thank you. Bye-bye.
Thank you very much. Have a nice day. Bye.
Goodbye.
Thank you.
Goodbye.
Bye-bye.
Bye.